Don't have any infrastructure. They don't want to set up. The last node consent, correct?
Yes, we're waiting on this.
I'm not going to sit here. I don't think there's anything on the agenda. Are you going to say that this morning? Or
It's a new update waiting. Yeah. Well, it's more politically correct report.
Right.
Okay.
Is that going to come up during?
I have a slide.
Is that going to be in the status? Okay, fine. Then what I'll do is I'll wait for status, but then I'll display because I don't.
Yeah.
Okay. I just want to make sure. I don't want Allison to say no. So, will you guys? Or do you want me to do that, or IRTF?
Both. Well, she's not here. She has medical emergency.
I'm sorry to hear that.
She's like in the hospital.
Yeah. Wait, with her father or her brother?
Father.
Okay, fine. That's a one-off. That's okay. Okay.
But in general, she's not.
Correct.
But that's not for here.
That's all.
Yeah.
Something for you? Can I fix something for you?
Yes.
And then boom. And so now it's actually.
How do I? Oh. Okay. Can I go back to the?
Yeah.
So, Stephanie, are you walking around and embarrassing all these people?
Oh yeah. Thank you.
The technology.
No, it's
Actually, we'll go with that. Right. Is that your job today? Is to embarrass those?
It is.
Good morning, everyone. So this is Crypto Forum Research Group meeting. So if you are here for CFRG, please take a seat. Thank you. So I'm Alexei, and my co-chair Kenny is not here, so maybe he's present online. Let's do a quick agenda bashing, just to double check. So I'll talk about status of documents and a few other things. Then we'll have 3 presentations on 2 active working group documents and 1 potential research group document. Okay. Agenda. So I hope you've seen Note well. We follow the same Note well as IETF. So we have minutes taker, we have Jabber relay to microphone person. Thank you both. I'll quickly talk about document status. So at the moment, we don't have any RFCs published since last IETF, no documents in RFC editor's queue. But chairs mostly cleared the backlog of Shepard's review so far. We have 2 documents in IRSG review. Magru hash signatures got 1 IRSG review. The comments were addressed, so this is now waiting for full IRSG review. And Rekeying is waiting for initial IRSG review. We have 3 documents nearly done. Aspect 2 waiting for Shepard's review. Kenny agreed to review the documents, so hopefully he will do this. I think he said about a month, so that should happen very soon. The other 2 documents, they are currently expired. We sent comments to document editors. They are revising documents based on feedback. So hopefully this will be updated soon, and then we'll send them to IRSG for review. And at the moment, we have 4 active documents. We'll have presentations on a couple of them, on hash-to-curve and randomness improvements. The other thing is, Kenny and I was asking for volunteers to serve as the 3rd CFRG co-chair. I think we selected the shortlist. At the moment, this is being finalized. So sorry, I don't have specific news at this point, but we're trying to get closure on this very soon. With this, just looking at how many documents we've finished recently and active documents, Kenny and I decided that we would like to do PEC selection process. Hopefully we'll come up with a single PEC out of this process. It should follow RFC 8125, which set some requirements or requirements on documentation. That was already done in this research group. Suggestions how to go about this process are very welcome. Please send them directly to chairs. What kind of questions you think we should ask when we were working on elliptic curves? We were asking questions to help narrow down on specific choices. So if you have a good set of questions, that would be great. We're also hoping to involve crypto review panel to compare proposals if there are multiple proposals and come up with recommendations.
So Martin Thompson, thank you for doing this. My only suggestion is pick a date and make it soon, please.
Okay.
I have a need for this.
We can discuss your desired date offline.
Hi, Stephen Farrell. I would have a suggestion is to replace the 1 or more with 0 or more.
Thank you, Stephen. Your opinion is well noted. Right. I think I'm done with chair slides. Oh, yeah. Go on.
Strike the or more. Just pick one.
Yes, I think in ideal world we would like to have 1, and if we fail, then we'll have 0. But I'm just not trying to limit ourselves, in case we really have a deadlock, and there are 2 packs that are, have slightly different qualities that we can recommend for different things.
So Martin Thompson, just to add to what Rich said, I want 1, and I don't want 1 with 500 tuning options that I can set in.
Yeah, I understand.
Settings,
I understood.
right? So pick something, yeah.
My name is Han Xin, AIST. As you know, there are several PEC protocols were published as RFCs. For example, the Dragonfly was published as RFC 7664, JPEG is RFC 8236, SES PEC Pro is RFC A1CC. These protocols were published from after concerning from the CFRG. My question is that actually I don't know what is the purpose of this PEC selection process. If a PEC that was already published as RFC was selected as for this from this process, what kind of RFC documents should the PEC be?
Right. So that's a good question. So I haven't consulted with Kenny. My opinion that PECs that we already published as RFC, they sort of, you know, obviously I don't have a time machine, I cannot go back, so they're already done. Whether we can select one of them and recommend it again as a result of the selection process, that might be so. I don't know. I don't want to prejudge the results. We don't know yet. So yeah, I think it's a good question. We'll need to think about that.
Thank you very much.
Thank you.
Paul Hoffman, who I think this is the first time I've come to the mic to agree with Stephen Farrell. But going to with what you just said, if the result of this is going to be a document that simply says, we think that thing is the best one, or that one with certain things, or none of them, that's just fine. But I haven't heard before this that this is going to be a separate document or decision or whatever. And I don't know how that works in a research group, but I know that people—
I don't know either.
Okay.
We're doing it for the first time this
right.
way, so.
Well, and it's just that we have, as the previous speaker said, we have a bunch of PECs as RFCs. There's a lot of questions about what does that mean? And so we're going to have to be sort of careful about it. I still think that 0 might be the right answer to say, we couldn't pick one. You know, make your best guess, and here's the list of the ones we have now. And that list is going to grow. I mean, this group has been pretty bad at saying no more PECs.
Hi, Rich Sauls. I know this is more time than you wanted to spend on this. The parallel I draw is we had lots of elliptic curves before, and we were able to pick a small number that were like, these are the ones we want. And it seems to me that the PEC situation exactly parallel to this. So I support.
That's sort of what I had in mind. But as I said, you know, we cannot back in time. And, you know, the PECs which are already published, we don't, you know, we might not want to say anything about them. We'll figure it out.
Recommended or no comment.
Yeah. All right. Thank you. And on this, let's start with the first presentation. Oh, no.
Good morning, everyone. Stanislav Mushlev, CryptoPro, and this is a status update for randomness improvements for security protocols draft. This is a joint work with Kes Kremers, Luke Garrett, Nick Sullivan, Christopher Wood. So, a quick reminder what it's about. The motivation has been the following: that since we may have some problems with PRNGs, such as bugs, backdoors, some problems with hardware RNGs that are used to initialize the initial state of PRNG, and some vulnerabilities with joint entropy pools. So we might want a safety net to avoid system compromise, so some backup for our PRNGs, and to propose some construction that is always better used than not used with the current PRNGs. So the idea here is to base on Nexus Streak, but since there are some technical problems, such as in real world, we usually don't have a direct access to private keys. We only have APIs to use them for some purposes. And since it's not a good cryptographic practice to use long-term keys outside of their primary scope, we should pick the construction very carefully, and we should make a lot of very clear security recommendations here, and we should get strict security proof for this exact construction. So the objective is to provide one ready-to-use solution with full security proof, with a model that exactly addresses practical security model, and so just have one RFC with one construction, maybe with some agility on algorithms, on basic algorithms. So the construction has evolved a little since we started this work, and now it looks like the following. So if you have some PRNG G, then we can define a PRNG G prime using expand and extract function, hash function, signature function, and two values of tag1 and tag2, where tag1 is a value that is needed to bind the construction to the environment, so to specific device, to protocol, maybe to MAC address or virtual machine user. And tag2 is some unique string that includes timestamp or counter, so it must be unique per one call of this G prime. So everyone who uses G in his applications can just change it to G prime, and it should become better. And the draft is why it should become better. So we have had a lot of changes, and one of most significant ones is connected with the virtual machines issue. It was there was a consideration by David McGrew on the list. It was really important issue about some problems with usage of PRNGs in virtual environments, and we've added 2 items to the bibliography and added several security considerations, several recommendations about how to use the construction if virtual machines are in scope. So these are 2 citations. So first of all, we strictly recommend to incorporate all known properties of an environment in the tag1, and secondly, that no security guarantees can be if the virtual machine is totally cloned without any differences, without any distinctions. So the constructions in this draft is not a silver bullet that can make magic if we can make a distinction between 2 virtual machines. Then we added some clarifications for weak initial entropy as additional motivation for usage with HSMs. What happens there? Oh, sorry, Martin.
Yeah, so Martin Thompson, I just wanted to clarify that if tag1 is duplicated, the consequence is that you produce duplicate random outputs, right?
That's a good question. In fact, if you just duplicate tag1, but you still have some guarantees of uniqueness with tag2, the security still remains. But in this case, you should have some way to provide uniqueness of tag2. And if tag1 and tag2 are both collided, then yes, there may be a collision of the whole G prime, because of when we use signature as a deterministic signature, you just have any differences between 2 cases.
Oh, I should have probably said it. You're back to GL as being your source of entropy, essentially.
Of course.
Does the draft say that? Because the text that you put up on the screen doesn't really say
okay.
that.
So if we have GTL that is broken, and if all these values collide, then we don't have any chance to be good. But if any one of these values differ, then it's proven, and I'll go to it later a bit, that the security can still be obtained. So virtual machines issue, then additional clarifications about another motivation for the work as weak initial entropy source. About usage with HSMs, there was some questions on the list. What happens where when you use the constructions with some keys stored in HSMs? Some additional recommendations about how to use it, about precomputations, about requirements for tag1 and tag2. We have added some recommendations that are really needed and that are used also in security proof later. Some minor changes about the terminology, about cleaning up usage of the words, so some minor changes. And I think that the most significant work since Montreal is about security proofs. I'll remind that the desired security properties that are declared in the draft and that must be proven are the following. The first 2 actually mean that the construction doesn't make anything worse. So first of all is a if some PRNG works fine, then the output construction will be fine, even if long-term keys are not secure anymore. And secondly, that we don't make any harm to the private keys because of our construction, so that we can use this. And as I said in the beginning, it's not good cryptographic practice to use keys in various scopes, but this is a property that we should address here. And the third is that the construction makes the world better, that if the PRNG is broken or controlled by the adversary, then the output will be indistinguishable from random if the secret key is still secret. So we've published a paper on ePrint, and we hope that we will evolve with this in the future to something and to some peer-reviewed journal maybe. So it contains full security proof of the construction, and I'll make a quick review of this. So to sum it up, the property number 2 is quite trivial one if all requirements that are mentioned in the draft are met. And we've had complete game hopping proofs for properties 1 and 3, so that PRNG makes it only better, with some assumptions and in a really strong adversary model. So in fact, we've proven everything in very strong assumptions about the adversary, even more strong than it's reasonable in practice. But we know some things that could be still improved. So the adversary model in one slide is that, of course, her aim is to distinguish an output from some random output, and she can do a lot of things. She can choose tag 1 and tag 2 on her choice. She can learn all values generated by the inner PRNG, except for the value she is attacking on. She can choose any number of output which she wants to attack and to distinguish it from random. And she can ask to reveal either the values generated by PRNG or the private key, but of course not both, because in this case we don't have anything secret. And so we really believe that the model perfectly reflects practice and even is much stronger than needed for practical assumptions, but we try to do this good. There are no issues with the proof in the random oracle model, but we thought that we can do better, and so we improved the proof, adding some additional assumptions to get rid of most unobvious problems with random oracles. So with assumption of that extract function is indistinguishable from random if one or another of its input is known, it must be pseudorandom. So there is an issue here, and I'll talk about it in the next slide, is that for HKDF we are currently using, the proof is only for 1/2 of this variance. So if X is fixed and Y is not, but not the other, or not vice versa. So we'll try to prove it or make minor changes to the whole construction to deal with this issue. And two other assumptions strictly follow from the recommendations in the draft, and they are quite obvious. So intermediate values must be kept secret, and that secret key is never used for values from the set of tag 1 values outside of the construction. So we had an objective of fully specified end construction that can be secure. Now we have complete security proofs in a very strong adversarial model without any unreasonable assumptions. The construction is quite specific, but we have some work to do. First of all, if we think which improvements should be done, first of all, as I said before, we have complete security proof for a KDF in general, but we want this to be proven as specifically as we can. So we should address the issue with HKDF because it wasn't proven for one quite reasonable, quite intuitively true, but it wasn't proven for one property. So we should try to do this. And we have performance issues with HKDF here. So thanks to Christopher Wood, we have some preliminary results of experiments. We have some numbers about reduction. It can be from 5 to 10 times slower than without this construction. And now we're thinking about whether we should do something else or whether we should leave it as it is, because as, for example, Kesk-Kramer thinks that it won't be a bottleneck in most applications. So it's one of the questions we still need to consider. That seems to be really important. So our current state and plan that the overall principles, overall structure, overall ideas of the proof and structure of the proof is completed. But we should make new experiments. We need to think about recommendations for specific protocols. We should improve the proof in 2 ways. First of all, to weaken limitations of the set of TAG1s, and to refine it for HKDF, the issue I was talking about the previous slide. And we hope to get a version addressing these issues until Prague. And yes, the questions are very welcome.
Valery Smyslov, LS+. Just a clarification, you use a signature to improve randomness. For those systems that don't use public key cryptography and rely on pre-shared key, is your technique applicable? So can you clarify?
Thank you very much for the question. Yes, actually, the same ideas are applicable, but the signatures there can be changed for any symmetric primitives. But as I said before, since we really want this to be quite a specific instruction, we needed to go not with a menu of choices, a menu of variants, but one specific instruction. Maybe we should think about adding some commands, what should be done if PSK is needed. I think that's a good question. So if you have PSK, yes, I think that's a good idea to address this. And I don't think it will be a real problem. Thank you.
Thank you.
Other questions, comments?
Quick comment, and I'm going to, it would cause a long discussion, so I want to do it on the list, but yes, a lot of people don't want to use a private key just willy-nilly, but it's so good here, and it wouldn't hurt to throw it in. I'm going to suggest later that you aren't so down on mixing in a private key if you happen to have one sitting around, and to include it in something else. So just wanted to bring that up, but I'll certainly bring it on the list.
Okay, thank you. Thank you very much. And I think that Christopher Wood wanted something to add about probable experiments with CKDF.
Right, yeah. So the initial experiments were just some kind of ad hoc ones that I did to get some sort of numbers. We're looking into other primitives like CKDF, like CMAC-based KDF to see if we can use things like AES intrinsics to speed this up. Recognize that that's not a RFC of any particular form. It's just a draft that Adam Langley wrote at one point and then abandoned. But it might be useful for this particular use case to help speed things up. So. And the security proof should ideally take that particular primitive into account.
Yes.
Yeah.
Okay. Thank you.
Right.
Any other questions, comments? No. Thank you.
Yeah, this should work.
All right, hello. We're going to talk about a draft that was adopted by the working group and is continuing to move forward about taking strings and mapping into elliptic curve groups. So as an overview for a review of this, the goal of this draft is to define some algorithms to efficiently map from a string to a point on a curve. This is for use in various high-level constructions, such as the VRF document that's going through CFRG, as well as various PAKEs require this, and different in various places you need to be able to map into a curve, and there's different requirements of what type of map. It can either have to be an injective encoding or potentially a random oracle encoding. So we're hoping to cover these cases, and this draft is meant to be a foundational piece to be plugged into a lot of these constructions going forward. So the current draft is at draft number 2. I'm going to go over the recent progress as well as open issues. So the first piece, after a lot of email on the list and some really good feedback from the working group, we got the feedback that this should be much more concretely defined in terms of taking this document and turning it into an algorithm and being able to deploy it. So rather than being descriptive of the mathematics, it should be very prescriptive in terms of exactly what to do. The first step in being able to take a string and hashing it into an elliptic curve point is often taking that string and hashing it into, or mapping it into the base field for that elliptic curve. And so we defined this explicit formula, which is a one-way hash from a string to element in the base field of the curve. This is deterministic and constant time are the important pieces. There were some flexibility earlier on in terms of different curves have different biases with respect to how you could take, however large the input is to mapping it into the curve field itself. So depending on the structure of the field, you can have different biases. So we're sure to clearly articulate how to reduce this bias so that it becomes negligible for any application. The second piece that was suggested was to give a concrete list of steps for various elliptic curves. And so in this, we decided to go with a cipher suite type of construction. So a list of 4 different pieces that put together will constitute a single hashing to curve algorithm. So this includes the destination group. So whether it's P256 or some of the CFRG standard curves, a specific hash to base algorithm that would make sense for that curve, a hash to curve algorithm, which is the most of the meat of the draft itself. There's different algorithms to consistently take an element of the base field and map it into the curve, and this is the heart of the document. And then optionally, a transformation afterwards. So as I mentioned earlier, some use cases of this construction have different requirements, some of which are that you're dealing with that the result of hashing into the curve is an element of a prime order subgroup of the elliptic curve. So there's different ways of doing a transformation at the end of the construction to make sure that you get something that does not have a cofactor. And also in some situations, such as the draft that I'll be talking about after this, VOPRF, and as well as the VRF draft that's currently going through, you need to have this act more like a hash function and not be reversible. So you should be able to have this look like a real hash function and not be reversible. So there's various options. There's something called FFSTV, which is essentially you do hash curve twice and add it together. And this gives you a random element in the curve. So this is something that's optional, not needed in all applications. So in terms of this overview, we put together a list of these cipher suites that correspond to the NIST curves. So there's only random oracle versions of that, as well as the CFRG curves in both the injective mode and the random oracle mode. So these are now in the latest version of the document. So there are some open issues. These were raised. There's a question about including pairing-friendly curves. So there's a construction by Fuku and Tabuchi about how to do this efficiently. And there's an open pull request on GitHub about a new cipher suite that is meant for BN256, which is a commonly used pairing-friendly curve. There are some questions about the security level of this specific curve, but this PR is under review. Another more important piece for these cipher suites that is not yet included in the draft is test vectors. So if someone were to make an implementation of this, they would need to be able to have inputs and outputs to check them against. So we're working on creating test vectors and validating them with multiple implementations of each of these cipher suites in various languages, as well as Sage. So open issues, there's a couple open issues that were raised on the list, as well as on GitHub, about some corner cases which, with respect to constant time. So for example, in Curve 448, in the Montgomery form, you don't have a complete addition formula. So we're considering changing the cipher suite for Curve 448 to use ED 448 because the Edwards formula has a complete addition formula. This helps make sure that it's constant time. There's a situation in SWU as currently written where if A equals 0, such as in the Bitcoin curve, for example, there's a division by A. So we have to fix that algorithm slightly. So there's a couple edge cases and corner cases with respect to the algorithm, and these should all be fleshed out once we have working implementations in multiple languages. Okay, so the next steps are, as I alluded to, complete the test vectors, review the pairing-friendly algorithm, and also review the other open issues, and make sure that these, if necessary, there's a constant time cipher suite for every single one of these use cases going forward. And yeah, that's the update on the hash-to-curve algorithm draft. Questions or comments? Okay, seems like no. So next we'll move on to something that I alluded to earlier, which is this is a proposed draft. This has not been adopted by the working group. It's something that we proposed 2 IETFs ago that builds upon some of the work that's going on right now in the IETF in the CFRG around VRFs, as well as hash-to-curves. So this proposal is called Verifiable Oblivious Pseudorandom Functions. So to give some intuition around this, VRF, this is something we're standardizing. This is somewhat equivalent of a public key version of a cryptographic hash function. So you can hash, and then you can verify that only the participant with the private key can hash. So this isn't exactly it. It's more like a commitment to a pseudorandom input, but this can be verified given a public key. And this is useful in a lot of cases. This is a foundational piece for, say, NSEC5 in the DNS world. There's another construction here called oblivious pseudorandom functions. This is kind of like a digital signature, and it works in a two-party relationship where someone who wants something signed can give it to the signer, they can sign it, and it can come back, and the value that they give to the signer is blinded, so that the signer does not have visibility into what the signature is of. So they know that they signed something, and then eventually you can verify that the signature is valid over the unblinded piece. So this is interesting this was used in, I guess, proposed in eCache systems, and it allows systems to sign information without having the knowledge of what it is. And there's a couple different places in which this is useful. So what is VOPRF? Well, it's kind of a combination of both VRF and OPRF. So it's a VRF for which the signer is blind to what they're computing the VRF over. So very specifically, if you recall some of the definitions of VRF, this will make a lot of sense. This reflects this pretty closely. So it's several pieces. One is an algorithm to compute a hash and then a proof from an input given a private key. Then it's also an algorithm that, given a hash and a proof, you can compute a verification that this was generated by a specific private key associated with a public key. And the last piece, which is what makes this puts the OPRF into the VOPRF is, so yeah, both those initial pieces are commonly known for in VRFs, but the ability to compute the hash of an input from a hash of a blinded version of that input. So if you take an input and you blind it and you give it to the signer or the party who's computing the VRF, they can compute a hash and a proof that is publicly verifiable with the public key. And you can take that blinded value and unblind it, and then you will have a hash that matches what the VRF would be. So VRFs are deterministic. So this gives you the ability to take that hash, hand it back to the signer, and they can compute the deterministic signature on it again and make sure that it matches. So in essence, this is equivalent to what an OPRF does, in that you can give back the data to the signer and they can confirm that they previously signed something that was, say, the pre-image of this. What makes it different from of an OPRF is that it's only the signer that can verify this once you've unblinded it. So it's not publicly verifiable, it's verifiable by the signer itself. Yes, Richard.
Yeah, so I was just going to confirm understanding here in terms of which of these steps are oblivious and involve the signer. So it sounds like 1 and 3, the creation of the proof and the verification, both involve the signer.
That's correct. 1 and 3 involve the signer. Yeah, and so you can apply the algorithm 1 on either a blinded or unblinded output. If it's on an unblinded output, that's essentially a VRF. If it's on the blinded input, it's this.
What is the does the blinding mechanism become part of the final output, like, or is it just a private construction to the person who's requesting the computation, as in RSA blind signatures?
It's similar to RSA blind signatures in that it does become part of the output from the signer, but when you unblind it, it retains some sort of verifiable property.
Right, but I guess what I mean to say is, like, I understand RSA blind signatures, right? I don't need to. I get back, like, an RSA blind signature. I get back a signature over the input string, and I don't need to carry around the blinding factors in order to have a valid signature. I have an ordinary valid signature. Is that the same case here?
It's almost the same case. So as you see here, you get back a hash and a proof. When you unblind, you only get back the hash. So the proof is something that needs to be recomputed from the input by the signer in order to confirm the value of the hash. You lose the proof when you unblind. The proof is really what ties the original signature to the public key of the signer.
Okay, I'm going to make one more stab at this, and then if I don't understand it, sit down.
It's kind of like Diffie-Hellman, actually.
Yeah. I mean, so imagine the following construction where I supply you with a blinded. I supply you with a I don't know, random value. Sorry, I said the thing I want signed, or PRF, Voproofed, and I give it to you. I blind it. I get an RSA blind signature back. That's the proof. And okay, never mind. I see that. I do.
Yeah. So yeah, in RSA blind signature, it becomes a valid signature that's publicly verifiable. In this case, that's not necessary.
Right, because the problem is I need to transform the signature in order to get that signature over the actual value, and that's the piece that's missing. Okay.
That's right. Yeah. So it's relatively close, but it's still very useful in that you can use it in a couple different applications that I'll go into right now. So just this diagram might be helpful for an overview of how it works. So you send a blinded message from the verifier to the prover. The prover computes a signature of S with M prime along with proof. And if you remove the blind, so you get back from M prime back to M, you can send M and the signature to the prover, and then they can then compute from M another signature and just check to see that the signatures are the same. So the main advantage of this is that the original transaction and the final transaction are not linkable together. So If you were to do this in bulk, and you would have the prover compute an VOPRF over a number of messages, you wouldn't know which one they would correspond to. So it could be anything that was sent as an input could have been the original signer. So if as this prover, you compute 100 million VOPRFs with the same key, you don't know which input actually corresponds to the verification. And this gives you the properties that you want, or at least the properties that I enumerated. So what this draft provides, well, specifically, there's a generic construction to do a VOPRF. What you need is a prime order group with a difficult discrete logarithm. You need a one-way map from a string to a group element of this group, and you need a discrete log equivalence proof. This is where the proof comes into place. And you can actually do a batch discrete log equivalence proof over an arbitrary group of this size using a Chaum-Peterson based proof. So the specific construction that we're presenting here in this draft is over a prime order group P256, which is the NIST curve, and then there's a potentially proposal to use CFRG curves, which, as I mentioned in the previous presentation, do not have a prime order group. So you have to make sure that when you're hashing into this group that you either eliminate the cofactor or use some sort of encoding that ensures that you're on a prime order subgroup of this curve. But just for simplicity, let's consider this P256. Then you have a hash to curve cipher suite, something from the previous draft I presented. And then you can use this construction, which is a batched Chaum-Peterson proof. This is from Ryan Henry's thesis in 2014, but it goes back to Chaum-Peterson proofs back in the day. So this is what's presented in the draft. What are the use cases? Well, there are many privacy-preserving applications. You could imagine interacting with the service and proving something that you're a member of a group, that you've performed a specific operation, and then returning to that same service and providing a proof that you had done this thing in the past, such that it's unlinkable. So the main inspiration for this was an application called Privacy Pass that we developed at Cloudflare. Privacy Pass is a way to solve one CAPTCHA on one site and get back a bunch of VOPRF outputs and then redeem them to solve other CAPTCHAs on other sites, so that your interaction with the first site is not known to the second site. It's just known that you did a proof of work of some type, specifically solving a CAPTCHA. There are other potential applications to this, privacy-preserving authentication, or I guess authorization. So you can imagine if you have a service, say you have a verified Twitter account or a Facebook account with a certain parameter, you could use that as a proof of belonging to a authorized set to a third-party service. So you could go, say, to your identity provider and do a VOPRF and then redeem that ticket with a third party, and they wouldn't know exactly which account you would correspond to, but simply that you're part of a specific set. There's applications we've looked into here for checking for compromised passwords. So you can use something like a VOPRF with a database of compromised passwords and kind of anonymously check to see if your password is in that database without leaking it to the database provider. And there's also, I've heard some potential applications here in proof of advertising, for example, online. So you prove to some service that you viewed an ad, and you can do so without leaking which ad that you saw. So here's some open questions I have before we go forward with this. Is a lot of the constructions here, a lot of the meat of this draft overlaps a lot with the VRF draft, but this draft includes two specific things on top. One is the blinding mechanism, and one is the batch verification mechanism that allows you to do multiple VRFs or VOPRFs at once. So maybe this is better suited as an extension to the VRF draft rather than a second complete draft in itself. But it's not clear to me that these features are really fit to be included in the existing VRF draft. And so this is sort of food for thought, and wondering if anybody has, anybody who's read the VRF draft and this proposed draft have any comments or thoughts on these questions.
Thank you very much, Nick. Stanislav Smyshlev, CryptoPro. Thank you very much for the presentation. I think that's really a really interesting construction. I've read both this draft and VRF draft, and I think that yes, they can be merged together, but I believe that here you have a lot of quite difficult questions to solve, and maybe it should be done as a separate work, just because of too many questions that Sharon and Leonid should address in their draft, and you should address in your draft. In any case, I'll be happy to help with reviewing this or reading this and making some suggestions. My personal opinion is that this draft should be separate, but in any case, I'll be happy to help with reviewing this. Thank you very much.
Great, thank you.
So Richard Barnes. So you said some things earlier that in certain cases, this you get kind of VRF as a special case of this. Is that the case, or am I misunderstanding a passing comment?
I believe so. I'd have to work out the details, but yeah, you get something VRF-esque if you don't, if you have a null blinding factor, for example.
Okay, so depending on how esque that is, I think it may be worth considering whether whether it would be close enough to merge the VRF into this as a special case, as kind of a subsection. So if you specialize in this way, then you get this other function that has some different properties. Yeah.
So just out of interest, I see hands of people who've read this proposed draft out there, just to get a sense of the room. So. Not too many. So I don't know how much we can do here at the mic, but eventually I'd like to ask the chairs to have a call for adoption for this draft, or to figure out exactly what the right combination of this and VR should be to move forward.
Yeah, we'll take it offline.
So just a quick question, and have you discussed this with Leonid and Sharon Goldberg about what they think about merging the drafts?
I haven't spoken to them about merging yet, but they're very aware of this proposal and the details of it.
And what do they think about these questions?
I think these questions address a different use case than the one that they're trying to address with VRF. I guess factoring out how these use cases overlap is something that we have not done together.
Mm-hmm. Okay, thank you.
Yeah, I don't think we need to decide here, whether it's a single merge draft or two documents. I think that's more of an editorial, but we can discuss it later.
I'm Son Xin, AISD. Thank you for the presentation. And I have one question about the use cases of VOPRF. You talked about the path of compromise checking. So could you explain more specifically how this use case works? Do you actually need a VOPRF, or I just thought that the OPRF could be enough to this case?
Right. OPRF may be enough for that case. That's true. But the VOPRF brings you an additional factor to it. I'd have to think about it offline. I'll get back to you.
Okay. Thank you.
All right, thank you. At this stage, we have 5 minutes left. So any other business, any other topics people want to bring up?
So I'll go a little preview of some work I've been.
What's your name?
Sorry, I'm Richard Barnes. I've been chatting with Karthik and a couple of other folks about doing some work on ECIES because we need this primitive for MLS for encrypting things to a tree full of public keys. So, you know, there's obviously already a kind of diversity of standards around ECIES, but nothing kind of widely implementable, freely available that has been through the rigor of this group. So I've got a draft in progress that I haven't posted yet, but if anyone would be interested in collaborating on, you know, encrypting to DH keys, I'd be interested to chat.
Okay. Do you have some suggestion, some draft already that?
I have a draft in progress that has not been posted yet.
Okay. Well, once it's posted, please let chairs know.
Just wanted to comment on that. Another use case for ECIS is for ESNI, and so I'm certainly interested in moving that forward, but at least for that particular problem.
Yeah, I mean, the sooner the better, because we have some like totally ad hoc construction, which I'm sure is completely awesome. And it'd be nice to like not have a totally ad hoc, completely awesome construction.
Okay, so I'm hearing there is some sort of urgency in. Okay, that's fine. Thank you. Any other questions, announcements? All right, thank you. Thank you for coming. I think we'll see some of you in Prague.